12 Lobes beneath Europa's icy shell is a saltwater ocean containing more liquid water than all of Earth's oceans combined. And it has been there, heated by Jupiter's gravity, for potentially billions of years. Subscribe if you want more of the cosmos. This is white space. Settle in. There is a place not far from where you are standing right now, measured in cosmic terms, where temperatures drop to 400 degrees below freezing, where mountains taller than anything on Earth rise from plains that have never known rain, where moons the size of small planets hide liquid oceans beneath shells of solid ice, and where worlds that look almost like ours have become utterly alien through the slow accumulation of small differences over billions of years. This place is our solar system, not some distant corner of the galaxy. Not a world light years away, it is here surrounding us. And the more we look at it, the stranger and more extraordinary it becomes. For centuries, the planets were points of light. Then the telescope made them disks, then surfaces, then worlds with weather and geology and moons. But it was only in the second half of the 20th century that we crossed the final barrier, that we stopped looking at other worlds and started visiting them. We sent machines, we accelerated them out of Earth's gravity well on columns of fire, aimed them across distances that take light minutes and light hours to traverse, and brought them into contact with surfaces, atmospheres, and phenomena that no human being had ever directly examined. The results were not what anyone expected. They were stranger, more complex, and more provocative than the most optimistic projections of the scientists who designed the missions. The Voyager spacecraft, 2 probes launched in 1977 on a trajectory that would carry them past Jupiter, Saturn, Uranus, and Neptune in sequence, set the template for what planetary exploration could accomplish. Voyager 1 and Voyager 2 together transformed our understanding of the outer solar system in a span of 12 years. They found active volcanoes on a moon of Jupiter. They found a moon of Saturn with a thick atmosphere and lakes. And then they kept going, moving outward through the heliosphere, crossing the boundary of the Sun's influence in the early 21st century and becoming the first human-made objects to enter interstellar space. Voyager 1, as of this writing, is more than 23 billion kilometers from the Sun, still transmitting, still returning data, the farthest any human creation has ever traveled. What follows is a journey through some of the most significant discoveries made within our own cosmic neighborhood, from the innermost planet to the frozen edge of the Sun's domain. Not distant stars, not hypothetical exoplanets. This right here, the planets and moons and small bodies orbiting our own Sun, and what we have learned about them from the machines we have sent to study them. The story is unfinished. It will remain unfinished for generations to come. But what we have already uncovered is remarkable enough to demand sustained attention. The machines we have sent out into the solar system carry instruments of extraordinary sensitivity, magnetometers, mass spectrometers, imaging systems, radar arrays, seismometers, and they have returned data measured in petabytes. Processing and understanding that data is the work of hundreds of scientists across dozens of institutions, and the process of discovery does not end when the spacecraft finishes transmitting. Papers based on Cassini data are still being published years after the mission ended. Results from Voyager's distant encounters are still being reanalyzed in light of new theoretical frameworks. The solar system we explore is not only out there in space, it is also in the archives, waiting to be understood by someone with the right question and the right tools to ask it. We begin not at the edge of the solar system, but at its innermost frontier, the small, scarred world closest to the Sun, a planet that was visited twice in the 20th century and largely forgotten until a second look revealed it to be far stranger than anyone had assumed. Mercury is the smallest planet in the solar system. It is also the densest after Earth and the least explored of all the rocky worlds. Only 2 spacecraft have ever reached it. Mariner 10 flew past it 3 times in 1974 and 1975, mapping roughly 45% of its surface, because the remaining 55% was in darkness during all 3 flybys. It remained unmapped for 3 more decades. NASA's Messenger spacecraft arrived in Mercury's orbit in 2011 and spent 4 years studying it in detail before its fuel ran out, and it was allowed to impact the surface in April 2015. Its final act, a planned collision with the planet it had been circling for 4 years. What those missions revealed was a planet that breaks several rules that planetary scientists thought were settled. Mercury's core is enormous. By proportion, Mercury has the largest metallic core of any planet in the solar system. The core makes up more than 80% of the planet's radius. The thin shell of rocky mantle and crust above it accounts for a startlingly small fraction of the planet's total volume. Understanding how Mercury came to have such a disproportionate core is an unsolved problem. The leading hypothesis is that Mercury was struck by a large object early in its history, and much of its outer rocky material was stripped away, leaving a core-dominated remnant, an origin story similar in some ways to the one proposed for Earth's moon. Another possibility is that Mercury formed close to the Sun in conditions that selectively incorporated iron over silicate rock. A third idea invokes the early solar wind evaporating lighter crustal material before the planet finished forming. No single theory fully accounts for all the observations, and the question remains open. Mercury's surface chemistry holds further surprises. Messenger mapped the distribution of elements across the planet's surface using X-ray and gamma-ray spectrometry, and found that Mercury's crust is unexpectedly rich in sulfur, potassium, and sodium, volatile elements that planetary formation models predicted should have been baked out of a planet that formed so close to the Sun. The presence of these volatiles in Mercury's surface rocks implies that Mercury either formed at a lower temperature than expected, or that volatile-rich material was delivered to it later by asteroid and comet impacts. Either way, Mercury's chemical composition does not match the models built to explain it, and every new piece of data deepens rather than resolves the puzzle. Mercury also has water ice. This was unexpected. The planet's dayside temperature can reach 430 degrees Celsius. But Mercury's axis is nearly perfectly upright. It has almost zero axial tilt, which means the floors of craters near the poles never receive direct sunlight. They are permanently shadowed, and in that permanent darkness, temperatures can drop below minus 170 degrees Celsius. Radar observations from Earth first suggested the presence of bright reflective material in these polar craters. Messenger confirmed it. The craters contain water ice, covered in many cases by a thin dark layer of complex organic material. The ice was deposited by comet or asteroid impacts over billions of years and has survived in the permanent shadows ever since. Mercury, the closest planet to the Sun and one of the hottest, is also a keeper of ancient ice, preserved in the darkest corners of its most ancient craters, while the sunlit terrain bakes at temperatures sufficient to melt tin. Messenger also discovered a class of surface feature found nowhere else in the solar system. Scattered across Mercury's surface are irregular depressions, ranging from tens of meters to several kilometers across, with flat floors and steep walls, surrounded by bright halos of material with unusual spectral properties. These features are called hollows. They appear to form when volatile material compounds that sublimate readily at Mercury's temperatures is exposed at the surface and evaporates away, leaving the hollow behind. Hollows are geologically young. Some may be forming today. They indicate that Mercury's crust contains a larger inventory of volatile compounds than any previous model predicted, and their presence rewrites the chemical story of the innermost planet. Messenger further discovered that Mercury is shrinking. As its enormous iron core cools, it contracts and the crust buckles and compresses in response, producing enormous thrust faults called lobate scarps, some of them more than 1,000 kilometers long and several kilometers high. These scarps are geologically young, and some researchers believe Mercury is still contracting today. Mercury is a planet simultaneously older than almost anything we can study, its surface preserving a record of bombardment from the early solar system, and actively evolving, its interior still cooling, its surface still deforming, its hollows still opening. The European-Japanese Bepi-Colombo mission is currently en route to Mercury and will arrive in 2026, carrying 2 orbiters with instruments far more capable than Messengers. The questions it will address include the origin of Mercury's anomalous core, the nature of the hollows, the chemistry of the polar ice deposits, and the detailed history of Mercury's geological and magnetic evolution. Mercury, overlooked for decades as a barren and uninteresting world, is turning out to be one of the most scientifically instructive bodies in the inner solar system. The hollows are also surrounded by material with anomalously high reflectance and unusual spectral properties that change over time, suggesting active sublimation occurring today. Messenger's extended mission, during which it lowered its orbit progressively closer to Mercury's surface until it impacted, returned images of the surface at resolutions below 10 meters per pixel in some regions, detailed enough to resolve individual geological features that no previous mission could have distinguished. The final data transmitted by Messenger in its last hours remain among the highest resolution images of Mercury's surface ever acquired. Now we turn to the world that has long held the title of Earth's twin, a title that in truth fits it very poorly. Venus is nearly identical to Earth in size. Its diameter differs from ours by less than 5%. Its mass is about 80% of our own. If you saw these 2 planets side by side from a great distance, you might struggle to tell them apart. But no 2 worlds in the solar system have diverged more completely from a common starting point. Venus is a place where the surface temperature reaches 460 degrees Celsius, hot enough to melt lead, where the atmospheric pressure at ground level is 90 times that at Earth's surface, where the clouds are made not of water but of concentrated sulfuric acid, and where it rains acid into air so dense it behaves more like a fluid than a gas. Nothing we have ever built could survive on the Venusian surface for more than a few hours. The Soviet Venera landers, the only spacecraft to ever transmit photographs from that surface, were built as armored pressure vessels, insulated against the heat and reinforced against the crushing pressure. They still lasted only about 2 hours each before being destroyed. The photographs they sent back are among the most haunting images in the history of planetary exploration. Flat, fractured slabs of rock extending to a hazy, overcast horizon, illuminated by dim orange light filtered through kilometers of dense, hot atmosphere. The rotation of Venus itself is strange. Venus rotates extremely slowly. So slowly that a Venusian day, measured from one sunrise to the next, is longer than a Venusian year. And Venus rotates in the retrograde direction, opposite to the direction it orbits the Sun, so that the Sun rises in the west and sets in the east. Why Venus rotates the way it does is unknown. The most popular hypothesis involves a large collision early in Venus's history that reversed its spin. But this idea does not account for all observations. Another possibility involves complex tidal interactions between the solid planet, its thick atmosphere, and the Sun's gravity that, over billions of years, could have driven the rotation to its current unusual state. The question of how a planet comes to rotate backward, once considered exotic, is now recognized as fundamental to understanding how planetary systems evolve. For a long time, before we sent spacecraft, astronomers imagined Venus as a lush, warm twin to Earth, a planet perhaps covered in jungle or shallow sea. The reality was something quite different. Venus is not a tropical paradise, it is a furnace. And understanding how it became one is among the most important questions in planetary science, because the answer tells us something essential about what can happen to a planet like ours. It tells us that the comfortable, temperate world we inhabit is not inevitable. Planets can fail. Habitability is not a permanent condition. A world closely resembling Earth in every structural measure can nevertheless become completely uninhabitable. The surface of Venus, hidden beneath its permanent cloud deck, was first mapped in detail by the Magellan spacecraft, which arrived at Venus in 1990 and spent 4 years scanning its terrain with synthetic aperture radar. What Magellan found was a landscape dominated by volcanic activity on a scale that dwarfs anything seen on Earth. More than 80% of the Venusian surface is covered by volcanic plains. There are shield volcanoes, lava channels stretching for thousands of kilometers, and a class of circular volcanic feature found nowhere else, called coronae, formed when plumes of hot material rise from the mantle and push the crust upward from beneath, then subside, leaving rings of fractured terrain. The largest corona, Artemis, spans 2,400 kilometers wider than the continental United States from coast to coast. There are also features called tesserae, highly deformed, ancient plateaus of buckled and folded terrain that may represent the oldest surviving surface material on the planet, preserving a record of Venus's early history that nowhere else retains. One of the most striking aspects of the Venusian surface is what it lacks. There are very few impact craters. On the Moon, on Mars, on Mercury, ancient craters cover the terrain in dense, overlapping fields. Venus has fewer than 1,000 craters across its entire surface, an extraordinarily low number for a body of its size and age. This absence tells a story. At some point in the past, perhaps between 300 million and 500 million years ago, Venus experienced a global resurfacing event. Volcanic eruptions, possibly catastrophic in scale, covered the old terrain entirely, erasing the crater record and laying down the landscape we see today. There are competing theories about what caused this. One holds that Venus lacks plate tectonics and that heat therefore accumulates in its interior until it reaches a threshold, then releases catastrophically in periodic volcanic paroxysms separated by hundreds of millions of years. Another suggests the global resurfacing was a one-time event, not recurring. A third holds that resurfacing is happening slowly and continuously at a rate too low to accumulate craters. The European Venus Express mission, which orbited Venus from 2006 to 2014, revealed specific locations on the surface that were significantly warmer than their surroundings, consistent with recent or ongoing lava flows supporting the idea that Venus is not geologically dead. What triggered the large-scale resurfacing, whether it happens repeatedly, and whether the planet is still actively reshaping itself, remain open questions. What is clear is that Venus lost its water. The early Venus may have had oceans. The ratio of hydrogen isotopes in its atmosphere suggests that vast quantities of water once existed there and were gradually stripped away by solar radiation once the runaway greenhouse effect began. Without oceans to absorb carbon dioxide and lock it into rock, the atmosphere thickened, temperatures rose, and the cycle accelerated. The result is the inferno that exists today. Venus is the clearest example in our solar system of a runaway greenhouse, a state from which no natural mechanism can pull a planet back. The timing of when Venus lost its water matters enormously. If the loss happened very early, Venus may never have been habitable. If it happened later, Venus may have had billions of years of liquid water on its surface, possibly more than enough time for life to arise. A modeling study suggested Venus could have remained habitable until as recently as 700 million years ago. That is well within the time frame during which complex multicellular life was already flourishing on Earth. The question of whether Venus was ever inhabited is not absurd. It is scientifically serious. Venus's cloud layers are organized in distinct altitude bands, each with its own chemistry and dynamics. The lower clouds, between 45 and 50 kilometers altitude, are composed of large sulfuric acid droplets. The middle clouds are a mixture of smaller droplets and sulfur particles. The upper haze above 65 kilometers is composed of submicron acid droplets and sulfuric acid ice. At around 50 kilometers altitude, the temperature and pressure on Venus are surprisingly Earth-like, approximately 60 degrees Celsius and 1 atmosphere. This is the region where some researchers have proposed, seriously though speculatively, that microbial life might survive, using the dense acid clouds as a habitat in the way that some Earth microbes survive in similarly acidic environments. A 2020 paper claimed the detection of phosphine gas in Venus's upper atmosphere at concentrations that could not easily be explained by known chemistry, a finding that, if confirmed, would have required a biological or unknown geological source. Subsequent reanalysis of the data questioned the statistical significance of the detection and reduced the inferred phosphine concentration substantially. The question of whether trace phosphine is present remains unresolved. Whether any process, biological or not, could produce it at Venus's atmospheric chemistry is an active area of research. 3 new missions are in development to address these questions. NASA's Da Vinci, which will send an atmospheric probe plunging through the Venusian clouds. NASA's Veritas, which will map the surface with far higher resolution than Magellan, and ESS Envision, which will combine radar mapping with spectroscopic to characterize the chemistry of the surface and atmosphere. Venus, long overshadowed by Mars in public imagination, is returning to the center of planetary science within this decade. Beyond Venus lies Earth, and beyond Earth lies Mars. And the story of Mars exploration is long enough to fill several narratives on its own. But there is another world on the far side of Mars that rarely receives the attention it deserves, the asteroid belt and the largest bodies within it. The Dawn spacecraft, launched by NASA in 2007, was designed to visit the 2 largest objects in the asteroid belt in sequence, something no previous mission had attempted. Its first destination was Vesta, a large rocky body roughly 500 kilometers across, which Dawn reached in 2011. Its second destination was Ceres, the largest object in the asteroid belt and the only one large enough to be classified as a dwarf planet, which Dawn reached in 2015. By orbiting both bodies, Dawn transformed 2 telescopic points of light into known worlds. Vesta is a remnant protoplanet, a body that formed in the early solar system and came close to becoming a full planet before the gravitational influence of nearby Jupiter disrupted the process. Its interior differentiated, a heavy iron nickel core sank to the center, a rocky mantle formed around it, and a basaltic crust formed on the outside, just as happened with the terrestrial planets. Vesta's surface records an extraordinary history of violence. Its southern pole is dominated by 2 enormous impact basins, Venenea, roughly 400 kilometers across, and Resilvia, roughly 500 kilometers across, whose central peak rises 22 kilometers from the basin floor, making it one of the tallest mountains in the solar system. These impacts, occurring hundreds of millions of years apart, excavated material from deep inside Vesta and scattered it across the inner solar system. We know this because a family of meteorites found on Earth, the head meteorites, Howardites, Eucrides and Diogenites, match the spectral signature of Vesta's surface and appear to be fragments blasted off by these impacts. Vesta has been raining pieces of itself onto Earth for billions of years, and we have been unknowingly collecting them. Ceres is a different kind of object entirely. While Vesta is rocky and dry, Ceres appears to contain a significant inventory of water ice, either in its interior or mixed into its crust. Dawn's instruments found that Ceres' surface contains ammoniated clays, minerals that incorporate ammonia into their structure, and that could only have formed in the very cold outer solar system, far beyond the asteroid belt. This suggests that Ceres formed much farther from the Sun than it currently orbits and migrated inward, or that material from the outer solar system was delivered to it by impacts. Either way, Ceres does not belong entirely to the dry inner solar system. The most striking discovery at Ceres was a set of bright spots inside a crater called Okator. From a distance, the spots appeared as brilliant white reflections against the dark, ancient terrain. As dawn moved closer, they resolved into multiple distinct features concentrated in two bright areas. Spectral analysis identified the bright material as sodium carbonate, a mineral that on Earth forms in evaporating saltwater brines. The most convincing interpretation is that Ceres has a subsurface reservoir of briny water that occasionally reaches the surface, perhaps forced upward by impacts or geological activity, and evaporates in the near vacuum, leaving behind salt deposits. Ceres, the largest body in the asteroid belt, the body that was demoted from planet to asteroid in the 19th century and then promoted to dwarf planet in the 21st, is still geologically active in the present day, and it may contain liquid water beneath its surface. The sodium carbonate deposits in Okator crater were found by Dawn's framing cameras to be significantly brighter than the surrounding terrain, and to be concentrated in two distinct zones: a central bright area called Cerealia Facula, and a cluster of smaller bright spots called Vinalia Faculae that correspond to different geological structures. The central deposit sits above a fracture system consistent with a brine reservoir beneath the surface, forcing material upward through cracks. Ground-based telescopes detected transient plumes of water vapor rising from Ceres' surface, concentrated near the bright spots, further supporting the idea of ongoing activity. Ceres' interior may contain a layer of liquid brine at depth maintained by residual heat from radioactive decay or from the impact that created Okator crater itself, which deposited enough heat energy to melt subsurface ice and sustain a liquid reservoir for thousands to millions of years. Beyond the asteroid belt, the solar system changes character entirely. The rocky, dense, relatively small worlds of the inner solar system give way to the gas giants and ice giants of the outer system, worlds of immense size, complex atmospheres, and vast families of moons. The largest of them, Jupiter, is more than 11 times wider than Earth and contains more mass than all the other planets combined. Jupiter has been studied by spacecraft since 1973, when Pioneer 10 became the first probe to pass through the asteroid belt and approach the giant planet. Voyager 1 and 2 followed in 1979, revealing the complex cloud bands, the Great Red Spot, and the volcanic activity of Io. The Galileo spacecraft orbited Jupiter from 1995 to 2003, dropping a probe into the atmosphere and conducting the first detailed study of the Galilean moons. But it was the Juno mission, which arrived at Jupiter in July 2016, that answered questions that had been accumulating for decades. Juno was designed to orbit Jupiter in a polar trajectory, passing over the poles on each orbit, rather than flying around the equator. This geometry gave it access to regions of the planet that no previous spacecraft had examined. What it found at Jupiter's poles was nothing like the banded cloud structure visible from Earth and from equatorial orbits. Jupiter's poles are covered in enormous cyclones, persistent storm systems ranging from several thousand to 15,000 kilometers across, arranged in geometric clusters. The North Pole has a central cyclone surrounded by 8 others arranged in a regular octagonal pattern. The South Pole has a central cyclone surrounded by 5 others in a pentagonal arrangement. These patterns are stable. They do not drift or merge or dissipate. The dynamics that maintain them are not fully understood. No general circulation model of Jupiter predicted anything like them. Juno has also mapped Jupiter's gravitational and magnetic fields with unprecedented precision, revealing that the planet's interior is far more complex than the simple layered model. A dense core surrounded by metallic hydrogen, surrounded by molecular hydrogen that planetary scientists had assumed. Jupiter's gravitational field is asymmetric. The northern and southern hemispheres do not match. This asymmetry implies that Jupiter's cloud bands extend much deeper into the atmosphere than expected, perhaps thousands of kilometers deep, and that the deep atmospheric flows influence the gravity field measurably. The metallic hydrogen layer, where hydrogen is compressed under such extreme pressure that it conducts electricity like a metal, begins at a depth of about 20,000 kilometers. It is this layer that generates Jupiter's enormous magnetic field, the strongest planetary magnetic field in the solar system, 14 times stronger than Earth's. Perhaps most relevant to questions about life in the solar system, Juno has been measuring the amount of water in Jupiter's atmosphere. This measurement matters because Jupiter's water content tells us about the conditions in the early solar system when Jupiter formed, how much ice and volatile material was present in the region where the giant planet grew. The measurement is technically difficult because water condenses deep in Jupiter's atmosphere below the cloud tops, and earlier probes were not able to measure it reliably. Juno's microwave radiometer can see deeper into the atmosphere than any previous instrument, and its preliminary results suggest that Jupiter's equatorial region contains more water than the Sun itself relative to other elements. This finding has significant implications for models of how the giant planets formed. Juno has also returned extraordinary images of Jupiter's cloud tops that have fundamentally changed how artists and scientists visualize the planet. The polar regions, invisible from Earth due to Jupiter's orientation, show a chaos of overlapping cyclones and anticyclones swirling at scales of thousands of kilometers, with blues and oranges and whites mixing in patterns that have no analog in the equatorial banding visible from Earth. The Great Red Spot, imaged at resolutions never achieved before, shows an intricate internal structure of smaller vortices and filaments that interact with each other and with the larger storm in ways that suggest the spot is maintained by a complex balance of energy inputs and losses rather than simply being a stable feature. Measurements of how the storm's size and color are changing over time. The spot has been shrinking for decades, indicate that the red spot's long-term survival is not guaranteed. Whether it will persist for another century or dissipate within a generation is unknown. No discussion of Jupiter is complete without its moons, specifically the 4 large moons discovered by Galileo in 1610 and now known to be among the most scientifically important bodies in the solar system. Io, closest to Jupiter, is the most volcanically active body in the solar system. Its surface, constantly being renewed by hundreds of active volcanoes driven by the tidal heating of Jupiter's enormous gravity. But it is Europa, the second Galilean moon, that has received the most intense scientific attention in recent decades. Io, the innermost of Jupiter's large moons, deserves attention in its own right. It is the most volcanically active body in the solar system, with more than 400 active volcanic centers identified from spacecraft imagery. Its volcanic output is so prodigious that its entire surface is geologically young. Old craters are buried under lava flows and sulfur deposits within thousands of years, making Io one of the few bodies in the solar system with essentially no visible impact craters, despite its 4 billion year history of bombardment. The heat source for this extraordinary activity is tidal. Jupiter's gravity, combined with the gravitational influence of the neighboring moons Europa and Ganymede that lock Io in a specific orbital resonance, flexes Io's interior on every orbit, generating heat through friction in the rock and generating the volcanic eruptions that make Io visible even from Earth through its sulfur dioxide plumes, which extend hundreds of kilometers above the surface. Some of Io's volcanic plumes are visible in telescope images from Earth as bright spots on the Moon's surface. The Galileo spacecraft in multiple close passes imaged lava lakes on Io's surface glowing at temperatures exceeding 1500 degrees Celsius, hotter than most terrestrial lavas, suggesting that Io's volcanism is partially sourced from deeper, more primitive mantle material than most Earth volcanism. When the Juno mission extended its mission to include flybys of the Galilean moons, it flew past Io at increasingly close distances, imaging the volcanic landscape at resolutions far exceeding anything from Galileo and discovering that the global pattern of volcanism is more complex and more geographically variable than previous imagery suggested. Europa is slightly smaller than Earth's moon. Its surface is covered in water ice, smooth, relatively uncratered, crisscrossed by a network of brown-tinged lines and ridges that give it the appearance from a distance of a cracked eggshell. The smoothness is telling. Europa's ice surface is geologically young, indicating that the surface is being continuously renewed. The lines and ridges are the result of tidal flexing. Jupiter's gravity pulls on Europa as it orbits, flexing the ice and generating heat in the interior. The same tidal mechanism that makes Io erupt volcanoes keeps Europa's interior warm enough to maintain a global liquid ocean beneath the ice shell. The ocean beneath Europa's ice is not a speculation. It is established by multiple independent lines of evidence. The Galileo spacecraft detected a perturbation in Jupiter's magnetic field as it flew past Europa, a perturbation that can only be explained by the presence of a layer of electrically conductive fluid beneath the surface. Salt water conducts electricity. Fresh water does not. The induction signal from Europa is consistent with an ocean that is global in extent and salty in composition. The ocean is estimated to be between 80 and 170 kilometers deep, containing more liquid water than all of Earth's oceans combined, and it has been there, maintained by tidal heating, for potentially billions of years. Europa's surface exhibits regions called chaos terrain. Areas where the ice has apparently melted from below, fragmented into large rafts, drifted apart and refrozen in new configurations, like pack ice broken up by a ship and refrozen. This process, called resurfacing by melt-through, may periodically bring ocean water into contact with the surface, allowing an exchange of chemistry between the ocean and the radiation environment above the ice. The surface of Europa is continuously bombarded by high-energy particles trapped in Jupiter's radiation belts, and that radiation drives chemical reactions in the surface ice, producing oxidants, including hydrogen peroxide and other reactive oxygen compounds. If these oxidants are transported downward into the ocean, they could serve as a chemical energy source for any organisms living there, much as atmospheric oxygen serves as a fuel for metabolism on Earth. NASA's Europa Clipper spacecraft launched in October 2024 and is currently en route to the Jupiter system, where it will arrive in 2030 and conduct approximately 50 close flybys of Europa. Its instruments include ice-penetrating radar to measure the thickness of the ice shell and the depth of the ocean, a mass spectrometer to analyze any material venting from the surface, cameras to map the surface at high resolution, and a magnetometer to characterize the ocean's electrical properties. Europa Clipper will not land on Europa. It will not drill through the ice, but it will characterize the ocean in sufficient detail to determine whether it has the chemical conditions necessary for life. whether the water is liquid, whether it contains the right elements, whether there is an energy source to drive metabolism. It will tell us whether Europa is worth the enormous investment that a future lander mission would require. Ganymede, the largest moon in the solar system, larger than the planet Mercury, is the third of Jupiter's Galilean moons and the only moon in the solar system known to generate its own magnetic field. This magnetic field, generated by convection in Ganymede's liquid iron core, creates a small magnetosphere embedded within Jupiter's much larger one. The interaction between the two magnetospheres produces distinct auroral belts at Ganymede's poles, observed in ultraviolet light by the Hubble Space Telescope. The periodic oscillation of this aurora, as Jupiter's magnetic field sweeps past Ganymede, was the key evidence that Ganymede, like Europa, harbors a saltwater ocean beneath its icy crust. Hubble observed that the auroral belts rocked back and forth less than expected in response to the changing external magnetic field, the inferred explanation being that a layer of electrically conducting fluid between the surface and the deep interior was dampening the response. Models suggest Ganymede's ocean may be enormous, sandwiched between layers of high-pressure water ice, potentially 800 kilometers deep, containing more liquid water than all of Earth's oceans several times over. The European Space Agency's JUICE mission, the J-Jupiter ICV Moons Explorer, launched in April 2023, and is en route to the Jupiter system, where it will spend several years studying Ganymede, Europa, and Callisto before entering orbit around Ganymede in 2034, making Ganymede the first moon other than Earth's own to be orbited by a spacecraft from another world. Europa's potential habitability depends not only on whether the ocean contains the right ingredients, but on whether it has the right energy budget. An ocean sealed under ice, disconnected from sunlight, must have another energy source to drive any chemistry complex enough to support life. On Earth, deep-sea hydrothermal vents provide this energy through chemical gradients between hot reduced chemicals emergent from the seafloor and the cold oxidized seawater around them. For this to work in Europa's ocean, the ocean must be in contact with a rocky seafloor where hydrothermal processes can occur. The thickness of Europa's ice shell is one of the most debated questions in outer planet science. Estimates range from a few kilometers to perhaps 30 or 40 kilometers. A thin ice shell would be more likely to have direct connections between the surface oxidants and the ocean below. A thick shell would provide better thermal insulation, but might limit the exchange of chemistry. Europa Clipper's ice-penetrating radar is designed to measure the shell thickness directly. The answer will determine what kind of future mission could practically access Europa's ocean. Beyond Jupiter, Saturn is the most visually distinctive planet in the solar system. Its ring system, visible through even a small telescope as a structure that does not look real, that looks like something placed there deliberately, is the first thing anyone wants to know about. But it was the Cassini spacecraft's 13-year orbital mission that revealed what the rings actually are, and the answer was far more surprising than anyone anticipated. Saturn's rings are made almost entirely of water ice, particles ranging in size from tiny grains to house-sized boulders, all orbiting Saturn in an extremely thin plane that extends 300,000 kilometers from the planet, but is in many places less than 10 meters thick. From edge on, the rings essentially disappear. This extreme thinness, combined with their enormous extent, makes Saturn's ring system one of the most geometrically improbable structures in the solar system. The rings contain an enormous amount of material, enough ice to build a moon roughly half the size of Mimas, but they are distributed across such a vast area that each cubic meter of ring contains almost nothing. What Cassini revealed in its final months the grand finale phase, in which the spacecraft was directed to pass between Saturn and the inner edge of the rings before its deliberate destruction in September 2017, was that the rings are geologically young not in human terms, but young in planetary terms. The rings formed somewhere between 10 million and 100 million years ago, long after the dinosaurs had appeared on Earth. This was shocking. The rings look so integral to Saturn that most scientists assumed they were primordial, as old as the planet itself. They are not something created them recently. The leading hypothesis is that a large icy moon of Saturn strayed too close to the planet and was torn apart by tidal forces, or that two moons collided and the debris spread into the ring plane. Whatever the cause, the rings are temporary. Saturn will not always have its rings. In another 100 million years or so, the rings will have largely dispersed, swept away by the combined effect of atmospheric drag on ring particles and a process called ring rain, in which charged ring particles spiral inward along magnetic field lines and rain down into Saturn's upper atmosphere. Cassini measured this ring rain directly and found that Saturn is losing roughly 10,000 kilograms of ring material per second. The rings of Saturn, which Cassini studied in unprecedented detail over 13 years, deserve separate attention. They appear from a distance as a thin, continuous disk, but Cassini revealed them to be a complex dynamic structure divided into distinct regions by gaps and waves. The main rings, A, B, and C, differ in their particle size distributions, their optical depth, and their composition. The B ring, the brightest and densest, contains so much material that radio waves can barely penetrate it. The A ring, separated from the B ring by the Cassini division, a gap maintained by a gravitational resonance with the moon Mimas, contains wave structures generated by the gravitational influence of Saturn's moons, their regular patterns making the ring look, in places, like a vinyl record. The ring edges are extraordinarily sharp. The A ring's outer edge is maintained by the moon Janus to within a few kilometers, where planetary ring theory would predict a gradual tapering over thousands of kilometers. In its final year during the grand finale phase, Cassini dove between the inner edge of the rings and Saturn's upper atmosphere 22 times, sampling material in a region that had never been directly studied. The data from these passes revealed that material is falling from the rings into Saturn's atmosphere at a rate of several thousand kilograms per second, a process called ring rain. At this rate, the rings would be consumed within 100 million years. Combined with other evidence for the rings' young age, this establishes that Saturn's rings are transient features, geological phenomena on a planetary time scale, not permanent accessories to the planet. When our Sun became a star, Saturn had no rings. When it eventually expands to swallow the inner planets, Saturn may have no rings again. We happen to live in the brief window when they exist. Saturn's interior, like Jupiter's, is incompletely understood despite decades of study. Cassini's gravity measurements during the grand finale revealed that Saturn has a diffuse fuzzy core, not a compact rocky nucleus, but an extended region where rock, ice, and dense fluid hydrogen gradually merge over a depth of tens of thousands of kilometers without a sharp boundary. This fuzzy core accounts for a surprisingly large fraction of the planet's radius, suggesting that the heavy elements that sank to Saturn's center during its formation have never fully settled into a compact structure but remain dispersed through the deep interior. The discovery challenges the standard model of giant planet formation, which assumed a compact core formed first and then accreted the surrounding gas envelope. Saturn's core may instead have formed by the direct collapse of gas and solids without a compact rocky seed, a process called pebble accretion, in which small particles gradually accumulate through gas drag without requiring a large initial nucleus. Understanding Saturn's interior through its gravity field, seismology, and ring dynamics is one of the continuing legacies of the Cassini mission, with new papers still appearing regularly. Cassini also made one of the most consequential biological discoveries of the space age. The moon Enceladus, small, just 500 kilometers in diameter, covered in fresh white ice, was found to have an active subsurface ocean that is erupting into space. From fractures near the South Pole, enormous plumes of water vapor, ice particles, and chemistry rise hundreds of kilometers above the surface and spray material into orbit around Saturn, feeding one of Saturn's faint outer rings, the E-ring, with fresh icy particles. Cassini flew through these plumes 17 times. Each pass refined the chemical inventory of the erupted material. The plume chemistry is extraordinary. It contains not only water and ice, but molecular hydrogen, a product of hydrothermal reactions between water and hot rock at the ocean floor. It contains silicon nanoparticles, particles that can only form in liquid water at temperatures above 90 degrees Celsius in contact with silicate rock. It contains carbon dioxide, methane, and complex organic molecules with masses greater than 200 atomic mass units, molecules that in terms of complexity and mass overlap with the range occupied by amino acids, lipids, and other biologically significant compounds. The picture that emerges from this chemistry is specific. At the bottom of Enceladus's ocean, liquid water circulates through fractured rock, is heated by the interior, undergoes hydrothermal reactions, and rises back toward the ice shell laden with chemistry. On Earth, this is precisely what happens at hydrothermal vent systems on the ocean floor, systems that support entire ecosystems in the absence of sunlight. The question of how long Enceladus has been erupting its ocean into space matters enormously. For the question of habitability, if the hydrothermal system has been active for billions of years, the ocean has had time to explore an enormous chemical space. Models of Enceladus's tidal heating suggest that the current vigorous activity may be episodic, that Enceladus cycles through periods of intense heating and quieter intervals as its orbital resonances with other Saturn moons shift. The current eruption phase may be geologically recent, but even a recent beginning means billions of years of prior, quieter hydrothermal history, time enough for chemistry to develop in the interior, even if the spectacular eruptions are new. To Titan, Saturn's largest moon is a world of a completely different character. Its dense nitrogen atmosphere, its rivers and lakes of liquid methane, and its vast accumulation of organic chemistry make it the most Earth-like world in the solar system in terms of surface processes, while being utterly alien in terms of chemistry and temperature. The Cassini mission spent years mapping Titan through its opaque orange haze, revealing a landscape with dune fields, river valleys, mountains, and seas. The Huygens probe, which descended through Titan's atmosphere and landed on its surface in January 2005, transmitted data for over an hour after landing the first and so far only time any spacecraft has operated on the surface of a world in the outer solar system. Huygens sent back images of a flat plane covered in pebble-sized rounded objects that appear to have been shaped by fluid flow rolled smooth by a river of liquid methane, deposited where they now sit by some past episode of flooding. Around them, the ground was darker and possibly damp with methane. The atmospheric measurements during descent revealed a complex chemistry of organic molecules at every altitude, with different compounds dominant at different layers of the atmosphere, a vertical stratification of chemistry that Cassini's orbital instruments could not fully resolve. The Huygens probe that descended through Titan's atmosphere on January 14, 2005, transmitted for 72 minutes during its descent and for an additional 72 minutes after landing on the surface, far longer than mission designers had planned for, since the probe's batteries were sized for descent only. and the lander's survival was considered uncertain. During descent, Huygens' gas chromatograph mass spectrometer sampled the atmosphere at multiple altitudes and identified dozens of organic compounds, complex molecules forming and condensing as ultraviolet radiation from the distant sun drove reactions in the nitrogen-methane mixture. The microphone on Huygens recorded the sound of Titan's winds, the only time any spacecraft has captured audio from the atmosphere of another world. The images from the descent camera showed a landscape of rounded pebbles on a flat plain, a drainage channel carved by liquid methane visible in the distance, a scene that required no caption to recognize as a place shaped by flowing liquid. The organic chemistry happening in Titan's atmosphere is the most complex, naturally occurring abiotic chemistry known outside of Earth. Ultraviolet radiation drives reactions between nitrogen and methane in the upper atmosphere, producing a rich inventory of organic molecules, not just simple hydrocarbons, but molecules containing carbon-nitrogen bonds, ring structures, and precursors to amino acids. These molecules condense and settle onto the surface over time, building up layers of organic sediment. Some researchers have proposed that the chemistry occurring in Titan's methane lakes at temperatures far below what we associate with biology might, under some circumstances, drive self-organizing reactions that share structural features with biological processes, not life as we know it, but perhaps a chemistry that, given time, could trend in that direction. This idea is entirely speculative, but it makes Titan a world unlike any other and the target of one of NASA's most ambitious current missions. The Dragonfly rotorcraft lander, scheduled to arrive at Titan in 2034, will bring this story to its next chapter. Dragonfly is designed to fly using Titan's thick atmosphere and low gravity to lift off, fly tens of kilometers, and land at a new location. It will sample the chemistry of Titan's dune material, the chemistry near impact craters, where the heat of the impact briefly created liquid water environments in which water-based chemistry could occur alongside Titan's usual hydrocarbon chemistry and the chemistry of the surface sediment. It is looking for evidence that the building blocks of life or their precursors are present in Titan's extraordinary organic inventory. Beyond Saturn, the solar system's ice giants, Uranus and Neptune, represent the largest gap in our observational record. Each was visited once by Voyager 2 and has not been revisited since. They remain the least understood major planets in the solar system. Uranus holds a distinction that no other planet shares. It rotates on its side. Its axis of rotation is tilted 98 degrees from the plane of its orbit, meaning that it essentially rolls around the Sun rather than spinning upright like the other planets. Its poles point toward and away from the Sun during its 84-year orbit, giving each pole 21 years of continuous sunlight, followed by 21 years of continuous darkness. This extreme seasonal cycle should drive enormous atmospheric dynamics. But Voyager 2's flyby in 1986 found an atmosphere that appeared remarkably bland, fewer visible cloud features than any other giant planet. More recent observations with the Hubble Space Telescope and large ground-based telescopes have found that Uranus becomes significantly more active as its equinoxes approach and atmospheric circulation changes, suggesting that the apparent blandness during Voyager's flyby was a seasonal artifact rather than a permanent condition. Uranus has 27 known moons, all named after characters from Shakespeare's plays and Alexander Pope's poetry: Ariel, Umbriel, Titania, Oberon, Miranda, and 22 smaller bodies. The 5 large moons, imaged by Voyager 2 in 1986, showed unexpected geological complexity. Miranda, the smallest of the five at only 480 kilometers in diameter, has one of the most geologically diverse surfaces in the solar system, a patchwork of terrains ranging from ancient, heavily cratered plains to younger grooved regions, with enormous parallel ridges and a cliff called Verona Rupes that plunges approximately 20 kilometers, one of the tallest known scarps in the solar system. How Miranda acquired such varied terrain is debated. One proposal suggests it was catastrophically disrupted by an ancient collision and reassembled under gravity in a random jumble of pieces. Another invokes past orbital resonances that drove tidal heating intense enough to generate localized geological activity. Ariel shows evidence of past resurfacing with relatively young smooth plains. Titania has a system of large rifts and valleys that may reflect the expansion of the interior as it froze. Oberon is covered in ancient craters and has a mysterious dark material at the bottom of some craters. The Uranian moons, studied only during a single flyby nearly 40 years ago, are among the most under-characterized major moons in the solar system, and there is strong scientific consensus that a dedicated Uranus orbiter and probe mission should be humanity's next major outer solar system destination. Uranus also has a magnetic field that is bizarre, even by the already strange standards of the outer planets. Its magnetic axis is tilted 60 degrees from its rotation axis, far more than any other planet, and the center of the magnetic field is displaced far from the planet's center closer to one side. The result is a magnetic field that is not simply a tilted dipole, but a complex, asymmetric structure that varies enormously from one part of the planet's surface to another. Understanding why Uranus and Neptune have magnetic fields so different from the other planets requires understanding what generates them. A question that points to the planet's interior, specifically to the layer of water, ammonia, and methane under extreme pressure that planetary scientists call the ice layer, even though it is not truly ice in any ordinary sense. This high-pressure fluid may be electrically conductive in unusual ways that produce the observed magnetic field geometry. Neptune was discovered in 1846, not by observation but by mathematics. The French mathematician Urbain Le Verrier and independently the British mathematician John Couch Adams both calculated from perturbations in Uranus's orbit that an eighth planet must exist and predicted roughly where it should be. When the Berlin Observatory pointed a telescope at Le Verrier's predicted position on the night of September 23, 1846, Neptune was there within 1 degree of where the equation said it should be. It was one of the great triumphs of theoretical physics applied to observational science. Proof that mathematics alone, applied carefully to data, could reach into darkness and find something real. Only one spacecraft has ever visited Neptune. Voyager 2 flew past it in August 1989. Neptune, despite being farther from the Sun and receiving less solar energy than Uranus, has a dramatically more active atmosphere. Its winds, measured during the Voyager flyby, exceeded 2,000 km per hour, the fastest sustained winds measured anywhere in the solar system. At the time of the flyby, a massive storm called the Great Dark Spot was visible in the southern hemisphere, comparable in scale to Jupiter's Great Red Spot. By the time the Hubble Space Telescope examined Neptune in the mid-1990s, the Great Dark Spot had vanished. New storms had formed elsewhere. Neptune's weather is volatile and unpredictable in ways that no model fully explains. Neptune's ring system contains one of the most puzzling structures in the solar system: incomplete ring arcs. 3 of Neptune's rings exist not as full circles, but as partial arcs. The Adams ring contains 5 distinct arcs spanning only about 40 degrees of the full 360. Ring arcs should be unstable. Differential orbital velocities should spread any concentrated clump around the full ring within years. The fact that Neptune's arcs have persisted for decades implies confinement by gravitational resonances with the small inner moon Galatea. But observations suggest the arcs are changing in ways that the resonance model does not fully predict, and the mechanism remains incompletely understood. Neptune radiates nearly 3 times as much energy into space as it receives from the Sun. Something internal, almost certainly the slow gravitational contraction of the planet and the differentiation of its interior, is generating heat at a rate that the calculations do not fully account for. Resolving this discrepancy requires an orbital mission. No such mission is currently approved. Neptune will not be revisited before the 2040s. Neptune's captured moon Triton, the only large moon in the solar system orbiting in the retrograde direction, is one of the strangest worlds we have ever observed. It was once a free object orbiting the Sun, most likely a Kuiper belt body that was captured by Neptune's gravity. The capture event released enormous heat, likely temporarily melting Triton's interior. Since then, Triton's orbit has been decaying. In 3.5 billion years, it will be torn apart or crash into Neptune. The surface Voyager 2 imaged includes active nitrogen geysers, pinkish organic terrain, and the cantaloupe-textured region unlike anything found on any other world. Thermal models suggest a possible subsurface liquid layer beneath the ice, maintained by residual heat from the ancient capture event. Mars is the most studied world beyond Earth and the most compelling candidate for ancient extraterrestrial life within the solar system. It is also the most visited. As of the mid-2020s more, spacecraft have successfully operated at Mars than at any other destination beyond the Moon. The picture of Mars that has emerged from this accumulated exploration is extraordinary. A world that was once warm and wet enough to support life, that maintained those conditions for potentially hundreds of millions of years, and that transitioned to the cold, thin atmosphere desert we observe today through a process that is still not fully understood. The surface of Mars preserves evidence of geological processes spanning its entire 4 billion year history, a record that Earth largely lacks because plate tectonics continuously recycles terrestrial crust. In the ancient southern highlands of Mars, craters dating from the late heavy bombardment period, the same bombardment that scarred Earth's moon, survive largely intact, giving planetary geologists a window into conditions 4 billion years ago that is simply not available on Earth. Superimposed on these ancient surfaces are younger volcanic deposits, Aeolian dunes, polar ice deposits, and in some regions layered sedimentary sequences recording the alternation of wet and dry periods over hundreds of millions of years. The dichotomy between Mars's ancient, heavily cratered southern highlands and its younger, smoother northern lowlands, a topographic difference of several kilometers between hemispheres, is one of the oldest unsolved problems in Mars geology. One hypothesis proposes a single enormous impact in the early solar system that excavated the northern hemisphere and reset its surface. Another proposes a long period of mantle convection that reshaped the northern crust from below. Neither explanation is fully satisfactory, and the dichotomy boundary where ancient terrain meets younger is one of the most geologically complex regions on the planet. The transformation of Mars from a potentially habitable world to a barren one hinges on the loss of its atmosphere. Mars today has an atmosphere so thin, less than 1% of Earth's atmospheric pressure at the surface, that liquid water cannot exist stably anywhere on the planet. Water on the Martian surface either freezes or evaporates almost instantly, depending on location and season. But the ancient valleys, lakebeds, delta deposits, and mineral assemblages preserved across Mars's surface tell a different story. They record a time when water flowed freely, when lakes filled craters and persisted for thousands to perhaps millions of years, when rain may have fallen and rivers carved channels hundreds of kilometers long. The question of what ended that era and when is one of the central questions of Mars science. The leading explanation is the loss of Mars's global magnetic field. Early in its history, Mars had a magnetic field. Evidence for this survives in ancient strongly magnetized regions of the southern highlands, where iron-bearing minerals were magnetized by a field that no longer exists. This magnetic field would have shielded Mars's atmosphere from the solar wind. The constant stream of charged particles flowing outward from the sun that in the absence of a magnetic field can strip atmospheric gas directly into space. When Mars's magnetic field failed, most likely because the planet's iron core cooled and solidified too quickly for the convection that drives dynamos to be maintained, the atmosphere became vulnerable. Over hundreds of millions of years, the solar wind eroded it. As the atmosphere thinned, the greenhouse warming effect that kept the surface above freezing weakened, temperatures dropped, and Mars became the frozen desert it is today. This narrative was confirmed and quantified by the Mars Atmosphere and Volatile Evolution spacecraft, MAVEN, which arrived at Mars in September 2014. MAVEN was designed to measure the current rate of atmospheric escape and characterize the mechanisms by which it occurs. Its instruments confirmed that the solar wind is the dominant driver of atmospheric loss, that charged particles from the sun collide with and accelerate neutral atmospheric gas molecules to escape velocity, stripping them away. MAVEN measured that Mars currently loses roughly 100 grams of atmospheric material per second to space. Over 4 billion years, that rate of loss varying as it does with the intensity of the solar wind and the position of Mars in its orbit could account for the loss of most of the ancient Martian atmosphere. The InSight lander's seismic measurements also recorded events that were not Mars quakes. On several occasions, InSight detected signals consistent with meteorite impacts. A seismic event followed after a predictable delay by the arrival of the acoustic wave through the thin Martian atmosphere. Subsequent orbital imaging confirmed the impacts, identifying fresh craters at the predicted locations. This allowed scientists to directly measure Mars's seismic wave velocities and use them to calibrate the interior model, a validation of the approach that was not anticipated when the mission was designed. InSight also detected a persistent low-frequency oscillation in the Martian atmosphere, a breathing of the planet related to the global dust cycle and the day-night thermal cycle, and found that the Martian magnetic field at the surface is variable on timescales of hours to days, reflecting local crustal magnetization patterns being distorted by external electromagnetic forces. Among the many spacecraft studying Mars from orbit, the Mars Reconnaissance Orbiter stands out for the sheer scope of what it has revealed about the planet's surface. Its HERE-EYES camera, the high-resolution imaging science experiment, produces images capable of resolving features as small as 25 centimeters from an altitude of 300 kilometers. Nothing like it has ever been placed in orbit around another world. Over nearly 2 decades of continuous operation, HERE-EYES has photographed vast areas of Mars at resolutions that reveal individual rocks, ripple patterns in sand dunes, tracks left by dust devils, and the wheel marks of rovers moving across the landscape. Some of HERE-EYES' most scientifically provocative images show features called recurring slope lineae, dark streaks that appear on steep slopes during the warm Martian seasons, grow longer over weeks and then fade when temperatures drop, only to reappear the following year at the same locations. When first documented, these features were interpreted as evidence of briny liquid water seeping through the subsurface and emerging at the surface in thin films, a finding that would have meant liquid water exists on Mars today. Subsequent analysis, including spectral measurements suggesting the streaks are associated with hydrated salts and granular flow patterns consistent with dry material behavior, has complicated that interpretation. The current consensus leans toward dry granular flows as the primary mechanism, but the connection between these flows and subsurface water or brine remains the subject of active investigation. Mars, even after decades of orbital study, continues to produce phenomena that resist simple explanation. MRO's ground-penetrating radar instrument, CHARAT, has added a subsurface dimension to this picture. Charat sends radar pulses through the Martian crust and analyzes reflections to identify what lies beneath. It has found extensive deposits of water ice in the mid-latitudes, buried under thin protective layers of rocky debris. These ice sheets, some hundreds of meters thick, contain more water than all the ice-free freshwater lakes on Earth combined. They were laid down during past epochs when Mars's axial tilt was different and polar conditions extended to lower latitudes. They are preserved today under their insulating rocky blanket, waiting. Future human missions to Mars may ultimately depend on these ice deposits as a resource. Charat has also mapped the polar layer deposits, the ice caps at Mars's poles, which are not simple blocks of uniform ice but complex, layered archives of past climate. Each layer represents a different epoch, with variations in dust content, ice crystal size, and chemical composition reflecting changes in Mars's orbit and axial tilt over millions of years. Reading these layers is directly analogous to reading ice cores drilled from Antarctica, which have yielded an 800,000-year climate record from Earth. Mars's polar archive potentially extends much farther back than that, encoding the history of a planet's climate evolution across billions of years, if we can learn to read it. The Curiosity rover, which has been exploring Gale crater since its landing in August 2012, has provided the closest and most detailed examination of ancient Martian habitability from the surface. Gale crater was selected as a landing site precisely because orbital data showed the presence of clay minerals in its layered sedimentary rocks. Clay minerals that form only in the presence of neutral pH liquid water, not in the highly acidic or alkaline conditions that would be hostile to most life as we know it. Curiosity's instruments confirmed this. The sedimentary rocks of Gale crater's floor record the existence of a freshwater lake, probably fed by streams flowing from the crater's rim, persisting for thousands to millions of years. That lake, 3.5 billion years ago, would have been chemically hospitable to the kinds of microorganisms we find in similar environments on Earth today. Curiosity's sample analysis at Mars instrument detected complex organic molecules in the ancient sediments, thiophenic compounds, benzene, and other carbon-bearing molecules that survived 3.5 billion years of radiation exposure in the Martian rocks, preserved by their burial below the surface. The detection of organics on Mars does not prove life existed there. Organics can be produced by non-biological processes, and some may have been delivered by meteorites. But finding them in the same rocks that record an ancient habitable lake, in concentrations that vary with rock composition in ways consistent with biological processing, keeps the biological interpretation alive and worth investigating. More puzzling is the methane. Curiosity's instruments have repeatedly detected spikes in the concentration of methane in the Martian atmosphere, a gas that should not persist in Mars's thin, ultraviolet irradiated atmosphere for more than a few hundred years before being broken down by photochemical reactions. Every detection of Martian methane implies a source that is producing it now on Earth. About 90% of atmospheric methane is produced by biological activity. The rest comes from geological processes, primarily serpentinization, the reaction of water with iron and magnesium-rich rock that produces hydrogen, and in the presence of carbon dioxide, methane. Curiosity detected a seasonal pattern in Martian methane concentrations, with higher levels in northern summer, which points to a regulated subsurface source releasing methane in response to temperature changes. What that source is, geological, biological, or something else, remains unknown. Curiosity's decade of exploration has covered roughly 30 kilometers of ground and climbed several kilometers in altitude up the flanks of Mount Sharp, the central peak of Gale crater, formerly known as Aeolis Mons, whose layered sedimentary rock sequences record billions of years of Martian climate history in the same way that geologists read Earth's rock record. Each layer Curiosity has crossed corresponds to a different depositional environment: lake sediment, wind-blown dust, river delta, evaporite salt flat. The transition from one to the next records changes in Mars's climate over millions of years. Among the most striking findings has been the detection of manganese oxide minerals in ancient sedimentary layers, minerals that on Earth form almost exclusively in the presence of free oxygen in the water or atmosphere. Finding them in 3.5 billion-year-old Martian rocks raises the possibility that the ancient Martian atmosphere was briefly oxygen-rich, or that oxidizing conditions in the ancient lake were more intense than current models predict. Where that oxygen came from, photosynthesis, atmospheric photochemistry, volcanic outgassing, is unknown. But the manganese oxides add another dimension to the picture of an ancient Mars that was chemically complex and, in at least some respects, surprisingly Earth-like. The Mars Insight lander, which operated from November 2018 until the end of 2022, approached Mars from a completely different angle. Rather than studying chemistry or geology, InSight was a seismometer mission. It placed a precision seismometer on the Martian surface and listened for Marsquakes. The goal was to use seismic waves to probe Mars's interior, its core size and state, its mantle structure, its crustal thickness, information that cannot be obtained in any other way. InSight detected more than 1,300 Marsquakes during its mission. Most were small, but a few reached magnitude 5 on a scale comparable to earthquakes, large enough to generate seismic waves that propagated through the interior. The data InSight returned allowed planetary scientists to construct the first direct model of Mars's interior structure. Mars's core was found to be liquid molten iron alloy, about 1,800 kilometers in radius, smaller than expected, and containing a higher proportion of light elements, such as sulfur, oxygen, and hydrogen, than pre-mission models had predicted. The crust was found to be thicker than expected, reaching 20 to 40 kilometers in the region around the landing site. The seismic measurements also found, somewhat unexpectedly, that Mars is seismically active, more active than the Moon, though less active than Earth. Something is still moving inside Mars, releasing strain in the crust through small but real Marsquakes. The planet is not completely dead. Perseverance, the most sophisticated Mars rover ever deployed, landed in Jezero crater in February 2021. Jezero is an ancient river delta, a location where a river carried sediment into a lake, depositing fine-grained material in precisely the environment, where on Earth organic material and microbial remains are most likely to be preserved in rock. Perseverance has been drilling into rocks, sealing core samples in titanium tubes, and depositing them on the surface for eventual collection. The mission's primary scientific goal is to identify the most biosignature-rich samples and cache them for return to Earth. Alongside its sample collection work, Perseverance conducted the first powered flight on another planet. Its technology demonstrator, the Ingenuity helicopter, made its first flight on April 19, 2021, a 12-second hop to an altitude of 3 meters, becoming the first aircraft to achieve controlled flight on a world other than Earth. Ingenuity was designed to make 5 flights. It made more than 70 before its final mission in January 2024, covering a total distance of more than 17 kilometers. Ingenuity demonstrated that aerial reconnaissance of Mars is possible, paving the way for future rotorcraft missions that could cover terrain inaccessible to rovers and reach destinations separated from safe landing zones by impassable terrain. The samples cached by Perseverance in Jezero crater represent the most consequential scientific investment in the history of Mars exploration. When they are eventually returned to Earth, currently planned for the early 2030s through a joint NASA and ESA Mars sample return mission, they will be analyzed by the full power of Earth's best laboratories, instruments orders of magnitude more sensitive than anything that can be sent to Mars, capable of detecting organic molecules at concentrations far below what Perseverance can resolve, capable of radiometric dating that will tell us exactly when the rocks formed and whether their chemistry was altered by biology. The answer to whether life ever existed on Mars may be waiting in those titanium tubes, sitting in a field in Jezero crater, as the planet's thin wind sweeps past them. Among the outer solar system's many discoveries, few have captured the public imagination as completely as the exploration of Pluto. For decades, Pluto was a fuzzy pixel, the most distant recognized planet, visible only as an unresolved point of light even to the Hubble Space Telescope, its surface unmapped and its moons only partially characterized. In January 2006, NASA launched New Horizons, a small, fast spacecraft the size of a grand piano, on a direct trajectory toward Pluto. The journey took 9.5 years. New Horizons arrived at Pluto on July 14, 2015. The images that came back over the following months rewrote everything. Pluto is not the dead, featureless ball of ice that everyone expected. It is a geologically complex world with towering mountains of water ice rising 3,000 meters above the surrounding plains, plains of flowing nitrogen ice that move like glaciers, a heart-shaped basin informally named Tombough Regio, after the astronomer who discovered Pluto in 1930, whose left lobe, Sputnik Planitia, is a vast plain of nitrogen ice several kilometers thick and roughly 1,000 kilometers across. The surface of Sputnik Planitia is divided into irregular polygonal cells, each roughly 30 to 40 kilometers across, that are maintained by slow convective overturning of the nitrogen ice, warm material rising from below and spreading outward, cooler material sinking at the cell margins. The nitrogen is moving. Pluto is geologically alive. New Horizons found mountains with unusual surface textures along their ridges and peaks, bladed terrain at high altitudes, consisting of sharp-edged fins and ridges of methane ice shaped by a specific erosion process in which sublimation preferentially removes material from particular orientations relative to the Sun. These bladed structures, some hundreds of meters tall, have no counterpart anywhere else in the solar system. They form because Pluto's eccentric orbit brings it periodically closer to the Sun, warming the surface enough to sublimate methane ice selectively. The resulting terrain looks like nothing carved by wind or water or gravity alone. It is a landscape shaped by the physics of sublimation and condensation on a slow, cold, enormous scale. Pluto has an atmosphere. It is thin, far thinner than Earth's, with a surface pressure about 100,000 times lower but complex. It is composed primarily of nitrogen, with traces of methane and carbon monoxide, and it extends much farther above the surface than anticipated. New Horizons detected atmospheric haze layers reaching 1,600 kilometers above the surface, well beyond what any model had predicted. The haze consists of complex organic particles, tholins, produced by photochemical reactions in the upper atmosphere, the same compounds that color Titan orange. Pluto's haze gives it a distinctive bluish tint in images taken looking back toward the Sun, as sunlight scatters off the tiny particles. Pluto's largest moon, Charon, is so large relative to Pluto that the two orbit each other around a common center of mass that lies between them, a true binary system. Charon's north pole is covered in a dark reddish material that New Horizons identified as tholins, the same organic compounds found in Pluto's atmosphere. The current hypothesis is that tholins produced in Pluto's atmosphere are carried by Pluto's tenuous atmospheric escape and deposited on Charon's pole, where the extreme cold traps them permanently. Charon is being slowly colored by Pluto's chemistry, a planet and its moon exchanging material across the void between them. The New Horizons flyby also revealed that Pluto's system includes 4 small moons beyond Charon: Styx, Nix, Kerberos, and Hydra. These moons orbit in a chaotic, tumbling manner. Their rotations unsynchronized with their orbital periods in contrast to the tidally locked configuration of most large planetary satellites. Their chaotic tumbling is thought to result from the complex gravitational environment created by the Pluto-Charon binary system. New Horizons imaged all four and found surfaces of varying brightness and color, with Nix and Hydra showing relatively neutral reddish hues, while Kerberos is darker. The system as a whole is thought to have formed from the debris of a large collision between two Kuiper belt objects early in solar system history, analogous to the formation of Earth's moon from the debris of a giant impact with the proto-Earth. Beyond Pluto, the Kuiper belt extends outward for tens of astronomical units, populated by thousands of icy bodies ranging from small chunks to dwarf planets. After its encounter with Pluto, New Horizons continued outward, and in January 2019 flew past a Kuiper belt object called Arrokoth, formerly designated 2014 MU69, at a distance of only 3,538 kilometers, the closest flyby of any solar system body by any spacecraft in history. Arrokoth is a compact binary, two roughly rounded lobes, each about 20 kilometers in diameter, that came together at such low speed, probably slower than a person can walk, that they gently merged rather than shattering. Its pristine, undisturbed surface indicates it has never been significantly heated, never been part of a larger body, and has been sitting in the cold outer solar system essentially unchanged since the first few million years of the solar system's existence. Arrokoth is as close as we can get remotely to seeing a pristine sample of the material from which planets formed. Among all the remaining mysteries of the solar system, one of the most intellectually dramatic is the possibility that our solar system's outer architecture may contain a large planet we have not yet found. In 2003, astronomers discovered Sedna, a body roughly 1,000 kilometers across, orbiting the Sun on an orbit so elongated that at its farthest point it reaches 84,000 astronomical units from the Sun, and at its closest it never comes closer than 76 astronomical units. Nothing in the known solar system should be able to sculpt an orbit like that. Sedna lives in an intermediate region between the Kuiper belt and the Oort cloud that existing models had not predicted. And Sedna is not alone. Subsequent surveys found other objects with similarly extreme detached orbits, bodies whose orbital orientations appeared to cluster in space in a way that chance cannot easily explain. The Kuiper belt itself has revealed far more complexity than the simple disk of icy objects originally envisioned when it was predicted by Gerard Kuiper in 1951. Modern surveys have found that the Kuiper belt is divided into distinct dynamical populations, the called classical Kuiper belt, whose members have nearly circular low-inclination orbits and extremely red surfaces, suggesting ancient organic material undisturbed since the solar system's formation. The hot classical Kuiper belt, whose members have more inclined and elliptical orbits consistent with having been dynamically stirred by the giant planets, and the resonant populations objects locked in precise orbital ratios with Neptune, the most famous of which is Pluto itself, which orbits the Sun exactly twice for every 3 Neptune orbits. These populations reflect different histories and different formation locations, and mapping them precisely is one of the main ways astronomers reconstruct the dynamical history of the early solar system. That history, according to the NICE model, named for the city in France where the research group was based, was violent. In the NICE model, the giant planets did not form in their current orbits. They formed closer together, in a more compact configuration, and the outer solar system was filled with a dense disk of icy planetesimals. Gravitational interactions between Jupiter, Saturn, Uranus, and Neptune, and between the giant planets and the planetesimal disk, eventually drove the giant planets to migrate outward. Saturn, Uranus, and Neptune moved outward. Jupiter moved slightly inward. As they migrated, Neptune swept through the outer planetesimal disk, sending planetesimals flying in all directions, some into the inner solar system, where they crashed into the Moon and created the craters we see today, some into the Oort cloud, and some into the Kuiper Belt's current resonant and scattered populations. The NICE model predicts broadly the structure of the outer solar system we observe today, including the location and composition of the Kuiper Belt, the orbital properties of the resonant populations, and the existence of the late heavy bombardment, the period of intense cratering in the inner solar system that left its mark on the surfaces of the Moon, Mars, and Mercury. It is not a perfect model. It has been refined and debated and modified many times. But it represents the most successful framework we have for understanding how the solar system arrived at its current configuration. The proposal that a large undiscovered planet, a world perhaps 3 to 10 times Earth's mass, orbiting the Sun at 400 to 800 astronomical units on a trajectory taking 10,000 to 20,000 years to complete, is gravitationally sculpting the orbits of these distant bodies, is supported by computer simulations and by several independent lines of observational evidence, including a subtle tilt in the solar system's plane relative to the Sun's equator. The planet, if it exists, would be extraordinarily faint at its current distance from the Sun and could easily have been missed by all previous sky surveys. The Vera Rubin Observatory, now operational in Chile, is designed in part to resolve this question. Its repeated high-sensitivity surveys of the sky will either accumulate enough distant trans-Neptunian objects to confirm the orbital clustering beyond statistical doubt, or they will find no such clustering and effectively refute the hypothesis. The answer may be only a few years away. Not all discoveries in the solar system come from planets and moons. Some of the most revealing encounters in the history of planetary science have involved small bodies, asteroids and comets, the remnants of planet formation. These bodies are scientifically priceless because they are ancient, pieces of the solar system's first few million years, preserved nearly unchanged for 4.5 billion years. The Japanese Aerospace Exploration Agency's Hayabusa 2 mission targeted an asteroid called Ryugu, a dark carbon-rich body roughly 900 meters across, shaped like a spinning top rotating once every 7.5 hours. The spinning top shape is thought to result from the Yorp effect, the gentle photon pressure of absorbed and re-emitted sunlight, which accelerates small asteroid rotation over millions of years until loose surface material migrates toward the equator and piles up in an equatorial ridge. Hayabusa 2 arrived in June 2018 and spent a year and a half mapping, studying and ultimately sampling Ryugu. It fired a copper impactor into the surface to create an artificial crater, then collected material from below the surface material shielded from solar wind and cosmic radiation since the asteroid formed. The samples returned to Earth in December 2020 contained water-bearing clay minerals, carbonate minerals, amino acids, and nucleobases, including uracil, one of the 4 information-carrying bases in RNA. These molecules, found in material from a body that has never been significantly heated and has never been contaminated by terrestrial chemistry, demonstrate that the prebiotic molecular inventory of life is not unique to Earth. It is synthesized throughout the solar system by the same physical and chemical processes that operate everywhere matter and energy interact. Ryugu has been delivering pieces of this chemistry to the inner solar system for billions of years, and pieces of it, or of bodies like it, have been landing on Earth since before there was any life here to receive them. NASA's OSIRIS-REx mission retrieved samples from a similar asteroid, Bennu, in October 2020. The return capsule landed in Utah in September 2023. Bennu's surface unexpectedly behaved like a liquid. When the collection mechanism touched it, the sampler buried itself nearly half a meter into the surface before the trigger fired, collecting far more material than the minimum required. Preliminary analysis found hydrated clay minerals, sulfide minerals, and carbon compounds. The mineralogy of a body that once existed in a warm, wet environment before being shattered and scattered. Comparing the chemistry of Ryugu and Bennu in detail is already revealing subtle differences that carry information about where in the early solar system each formed and what conditions they experienced. The European Space Agency's Rosetta mission accomplished something even more remarkable. It placed a spacecraft in orbit around a comet and operated it there for 2 years. Comet 77P Churyumov-Gerasimenko, a dark two-lobed body about 4 kilometers across with the consistency of a weakly packed snowball, was Rosetta's target. The two lobes of the comet are thought to be two separate bodies that collided at low speed and merged, just as Arrokoth's lobes merged. Rosetta deployed the Philae lander onto the comet's surface in November 2014, making it the first spacecraft to land on a comet. The landing was not clean. Philae's anchoring harpoons failed, and the lander bounced twice before coming to rest in a shadowed location that limited its solar power. But before its batteries died, Philae transmitted data from the surface, including the detection of organic molecules that had never been previously identified in a comet. Rosetta itself, in orbit, detected more than 500 distinct organic molecules in the comet's coma, the cloud of gas and dust that surrounds the nucleus as solar heating vaporizes its volatile ices. Among them was glycine, the simplest amino acid, and phosphorus, one of the 6 elements considered essential for life as we know it. The comet was found to be far less icy than expected. The dust-to-ice ratio was much higher than previous models had assumed, meaning comets carry more solid organic material and less water than the old picture suggested. The interior is extremely porous, about 70 to 80% empty space, more like a loosely packed cloud of material than a solid body. The boundary of the solar system itself is a subject of active research. The heliosphere, the bubble of space dominated by the sun's magnetic field and the solar wind, is not a fixed structure but a dynamic one, shaped by the pressure balance between the outflowing solar wind and the interstellar medium pressing in from outside. The boundary where the solar wind slows to subsonic speeds is called the termination shock. Beyond it lies the heliosheath, a turbulent region where solar wind plasma interacts with the interstellar medium. The outer boundary of the heliosphere, where the sun's magnetic influence ends entirely, is called the heliopause. Voyager 1 crossed the termination shock in 2004 and the heliopause in 2012, becoming the first human object to enter interstellar space. Voyager 2 crossed the heliopause in 2018 at a slightly different location, revealing that the heliopause is not a uniform surface, but a complex, variable boundary shaped by the local interstellar magnetic field and the sun's varying activity level. Data from both spacecraft in interstellar space have already revealed that the interstellar medium immediately outside the solar system has properties that ground-based observations had not fully anticipated. The heliosphere is smaller on its leading side, the direction toward which the solar system moves through the galaxy, than on its trailing side, where it extends into a long tail. Its exact shape is still being mapped by the Interstellar Boundary Explorer satellite, which observes the boundary remotely using energetic neutral atoms as tracers. The heliosphere is not merely the sun's domain, it is a shield protecting the inner solar system from the full intensity of galactic cosmic radiation. Understanding its structure and variability is essential for assessing the long-term habitability of any world within it. Beyond the Kuiper belt, at distances of 1,000 to 100,000 astronomical units, lies the Oort cloud, a vast spherical reservoir of icy bodies thought to be the source of long-period comets. The Oort cloud has never been directly observed. What we know about it is inferred entirely from the orbits of comets arriving from all directions with equal probability, suggesting a spherically distributed source. It is estimated to contain several trillion icy bodies. At that distance, the Sun's gravity is so weak that passing stars and the tidal force of the Milky Way perturb Oort cloud bodies onto trajectories that occasionally send them into the inner solar system. The Oort cloud is a direct link between our solar system and the galactic environment, a reservoir of primordial material whose dynamics are shaped not just by our Sun, but by the broader structure of the galaxy. The interstellar objects Oumuamua and Borisov represent the inverse, debris from other solar systems drifting through the galaxy, briefly passing through our neighborhood. Their detection within 2 years of each other by surveys sensitive enough to find them suggests interstellar space is full of such objects, that planetary systems routinely eject material into the galaxy, and that the organic chemistry of one system can literally visit another. In 2017, something arrived in the solar system from elsewhere. The Pan-STARRS Survey Telescope in Hawaii detected a small, rapidly moving object on a trajectory that was unmistakably hyperbolic, a path that no object originating in the solar system could follow. The object, eventually designated 1 Oumuamua, had come from interstellar space. It was the first interstellar object ever confirmed to pass through our solar system, and it behaved strangely. Its trajectory deviated from what gravitational forces alone would predict. It was accelerating in a way that could not be explained by the Sun's gravity or by standard cometary outgassing. No gas or dust was detected around it. It was elongated, much more so than any known solar system object, with a length-to-width ratio estimated at roughly 10:1. Astronomers proposed numerous explanations: an unusual comet releasing hydrogen gas invisibly, a fragment of a nitrogen ice planetesimal, a thin flat object pushed along by radiation pressure, something else entirely. No consensus was reached before Oumuamua accelerated out of the solar system, moving too fast for any mission to intercept. 2 years later, in 2019, a second interstellar object was detected. Comet Borisov, named for the amateur astronomer who discovered it, was more recognizable than Oumuamua. It had a clearly visible coma and tail, behaved like a normal comet in every measured respect, and allowed detailed spectroscopic study. Its composition, water ice, carbon monoxide, trace organics, was broadly similar to comets from our own solar system. Borisov appears to be a comet that formed around another star and was ejected from that system, just as many comets from our own solar system are ejected by gravitational interactions with the giant planets. Its composition tells us that the chemistry of comets, and by extension the chemistry being distributed across planetary systems throughout the galaxy, may be broadly similar from one system to another. The solar system is not chemically unique. The molecules that preceded life here are present everywhere, in the spaces between the stars. The asteroid belt is continuously being depleted by the Yarkovsky effect, a subtle force generated when an asteroid absorbs sunlight and re-emits it as thermal radiation from its cooler night side, offset from the absorption direction by thermal inertia. This tiny force, accumulating over millions of years, can shift an asteroid's orbit into one of the gravitational resonances with Jupiter that populate the belt's edges. Once in a resonance, the orbit becomes chaotic and can rapidly evolve into a Mars-crossing or Earth-crossing path. This is the primary mechanism by which main belt asteroids become near-Earth objects. The population of near-Earth objects larger than 100 meters now known numbers in the tens of thousands, with hundreds of thousands estimated above a few meters. In September 2020, NASA's DART spacecraft deliberately impacted the moonlet Dimorphos, orbiting asteroid Didymos, and changed its orbital period by 33 minutes, 10 times the minimum mission success criterion. The amplification came from ejecta momentum. The material blasted off by the impact acted as a rocket exhaust, multiplying the spacecraft's own momentum transfer. For the first time, humanity had demonstrably altered the orbit of a natural solar system body. Planetary defense is no longer theoretical. The solar system, the more we study it, begins to look less like a collection of isolated objects and more like a connected system. A system in which material flows between bodies, chemistry begun in one place is completed in another, and the conditions for life are neither rare nor concentrated in one location, but distributed throughout the whole structure. Water is not rare. Organic chemistry is not rare. The energy sources that drive biology, chemical gradients, tidal heating, radioactive decay are common. What remains unknown is whether any of this abundance has ever, in the 4.5 billion years since the solar system formed, produced anything that moves, feeds, reproduces, and adapts. We know that our solar system contains at least 5 recognized dwarf planets and probably hundreds or thousands more waiting to be identified in the Kuiper Belt and beyond. We know that liquid water exists beneath the ice of at least 3 moons, Europa, Enceladus, and Ganymede, and possibly several others. We know that complex organic chemistry is present throughout the system, on asteroids and in comets, and in the atmosphere of Titan, produced by the same ultraviolet chemistry and aqueous chemistry that operates wherever matter and energy meet. We know that Mercury has ice in permanent shadow, that Ceres may have liquid brines, that Venus may have been habitable until geologically recent times, that Mars was once wet and chemically complex for potentially billions of years. We do not know whether any of this has ever produced biology. We do not know whether the ocean of Enceladus contains microbes in its hydrothermal vent systems. We do not know whether Europa's ocean, which may have existed for billions of years and which contains the necessary elements and energy sources, has life in it. We do not know what the Perseverance samples will reveal when they reach Earth laboratories, or what Dragonfly will find in Titan's dunes, or what Bepi Colombo will discover in the chemistry of Mercury's hollows. We do not know whether a 9th planet is moving through the dark at the edge of the solar system, shaping the orbits of bodies we have barely begun to catalogue. We do not know what the interstellar visitors Oumuamua and Borisov actually were, or how many more such objects pass through our solar system every year, too small and too dark to detect with current technology. What we do know is that the answers are within reach. The missions are built or being built, the samples are cached or in transit. The telescopes are operational. The solar system we inhabit is one of the most studied and least understood places in the universe, and the gap between those two descriptions is narrowing year by year, one flyby and one landing and one sample return at a time. There is a pattern in planetary exploration that has held since the first spacecraft left Earth. Every destination, when approached closely enough, turns out to be stranger than the best model that preceded the mission. Mars was supposed to be like the moon, cratered, dead, simple. It was a world of canyon systems and ancient riverbeds and seasonal methane pulses. Jupiter's moons were supposed to be frozen, inert, and geologically simple. They were volcanically active, oceanically alive, and chemically extraordinary. Saturn's rings were supposed to be primordial remnants of the solar system's birth. They are 100 million years old, at most transient and temporary. Pluto was supposed to be a frozen, inert ball of ice. It had glaciers and mountains and bladed terrain and an escaping atmosphere, and the moon being slowly painted by its chemistry. The universe has not yet presented us with a destination that was less interesting than expected. This is not a small thing. Every generation of scientists inherits a solar system that is larger, stranger, and more chemically rich than the one their predecessors studied. The generation before the space age knew a solar system of 9 or 8 or however many planets you count, with moons that were interesting but geologically simple and small bodies that were regarded as debris. The generation of the Voyager era discovered that those moons were alive, volcanically, tectonically, oceanographically alive, and that the small bodies carried the chemistry of the solar system's birth. The current generation has found that water is everywhere, that organic chemistry is everywhere, and that the boundary conditions for life as we understand it are met in multiple places that we have yet to visit with adequate instruments. What the next generation will find, no one can say with confidence. But the pattern of the last 70 years, every new observation revealing more complexity, more habitability, more surprise than the model that preceded it, gives reason to believe that the next chapter will be as transformative as any that came before. It suggests that the processes that produce complexity, that produce geology and chemistry and the long molecular cascade that may, under the right circumstances, produce biology are not special to Earth. They are not rare. They are what happens when matter and energy interact over long time scales, and both matter and energy are plentiful throughout the solar system and throughout the universe beyond. The next discovery is already underway. Someone right now is examining data on a screen, data that arrived from hundreds of millions of kilometers away, traveling as a weak radio signal at the speed of light, received by the ground station antenna, decoded and calibrated and displayed in a form that the human mind can parse. And that person is seeing something that does not fit, something that requires an explanation, something that will, in time, become the next chapter in the story of this extraordinary system of worlds. A story that began 4.5 billion years ago, that has been unfolding in silence since long before any creature on Earth was capable of wondering about it, and that is still improbably and magnificently being written